Hello, everyone, and thank you very much to the organizers for this opportunity to speak. My name is Rose Kaplan-Kelly, and today I'll be talking about right-angled links and thickened surfaces. I'm going to start with some motivation. So first, we have this overarching question, which is how much can we learn about the geometry of a link's complement from the links diagrams? And a family of links that have been very helpful for this is the family of alternating links. So a follow-up question is, can we gain those same nice properties of alternating links for broader families of links? Another motivation behind this work is finding totally geodesic surfaces in link complements and investigating the possibility of right-angled knots. Throughout this talk, we'll be looking at generalized diagrams of links. So these are diagrams of links on closed surfaces with genus greater than or equal to 1. And here we have two examples of such links. So you can see the link in green on these surfaces here of genus 3 and here of genus 2. We'll say that these links are alternating on these surfaces if each boundary component of each region can be given an orientation so that crossings alternate between over and under. So if we look at this link on the right, we see that this fails that condition because we have here this crossing where my strand runs under and then runs under again. Whereas on the right, if we look at this region right here, we can see the condition is satisfied because the strand runs under, then over, similarly under, then over, etc. Throughout, we'll be interested in cellular weakly generalized alternating links. So that means that our links are reduced. So for any component of the link, there has to be at least one crossing. That rules out links such as this one right here that has this component with no crossings. Our links have to be weakly prime, which means that for any disk we have in our projection surface F, such that the boundary of the disk intersects our link diagram transversely twice. So here we can see the boundary of this disk intersects this link diagram transversely in two places. We want the intersection of that disk with the link diagram to be an embedded arc. So that rules out links like this one where we have this intersection that's not an embedded arc. And finally, we need our links to be cellular. So that means that every region is a disk. So that rules out links like this one again, because we can see that this region in our projection surface is not a disk. Part of why we want those properties for our links is that they'll guarantee that our link is checkerboard colorable. What this means is that we can color in the regions either white or shaded, such that with respect to any crossing, faces on a diagonal have the same coloring, while faces that are neighbors have different coloring. So an example is shown here. With this checkerboard coloring, we can then form two checkerboard surfaces for that link diagram. We do this by inserting a twisted band at each crossing that will connect faces with the same coloring. So to form the shaded checkerboard surface in this example, we'd insert twisted bands connecting all of these shaded faces at all of these crossings. And we do the same thing for all of the white faces to form the white checkerboard surface. Notice that these two surfaces are going to intersect precisely at each of those crossings. And they'll intersect in an arc that runs from the understrand to the overstrand at that crossing. Right? So we can see like here, this shaded checkerboard surface intersects this white checkerboard surface at some arc running from this understrand to the overstrand. And that's called a crossing arc. In order to study the complements of these links and thickened surfaces, we're going to need this notion of generalized polyhedra. So generalized polyhedron is a cone on the surface with a cellular graph on the boundary copy of the surface, so like this F cross 0. So here we have this cone on the surface, and we have a cellular graph here. We'll say that this generalized polyhedron is ideal if all of the vertices of that cellular graph and the vertex that we cone to have been removed. We can also say that it's ultra ideal if that vertex here in blue is ultra ideal. Our generalized polyhedron will be semi-truncated if that ultra ideal vertex has had a neighborhood removed. So we can chop off a neighborhood of that ultra ideal vertex. Howie and Purcell found a general topological decomposition of links in more general three manifolds than just thickened surfaces, but here we'll state this for thickened surfaces because that's our setting. What they found is that for our link, we can decompose the complement in the thickened surface into two generalized polyhedra. We'll call this P plus and P minus. To recover the full complement from this decomposition, what we do is we glue P plus to P minus by a homeomorphism, which is a composition of the identity with a rotation on each face of this boundary surface F with that diagram removed. So in this picture here, where we've zoomed in on one face, to recover that full complement, we glue P plus to P minus with a rotation, which you can see by this coloring on this face. We rotate this face and glue here. That graph corresponds to the original diagram of the link that we had on the surface F. And because we have this correspondence between these cellular graphs and that diagram, that also gives a correspondence between the checkerboard coloring we have for the link diagram and then a coloring we can put on P plus and P minus. So we can color in these faces from these cellular graphs on P plus and P minus, white and shaded, to match that checkerboard coloring on the link diagram. Another decomposition that we'll be interested in is this face-centered bipyramid decomposition. Here, for every face that we have in our original link diagram, we cone above and below to form a bipyramid centered on that face. So here we've looked at just one face in that link diagram with those strands drawn in yellow. We cone above and below to form this bipyramid. So all of these pink vertices here, which correspond to the strands, will be ideal. And then the blue vertices that we've coned to will be either ideal or ultra ideal, depending on if our surface had genus 1 or higher genus. If our projection was on a higher genus surface, we'll then truncate those ultra ideal vertices. So for every bipyramid we get for every face, we then truncate, so we get these two truncation faces. To recover the full complement from all of these bipyramids, we glue together the neighboring bipyramids. So that will also mean that all of these truncation faces have been glued together along their edges. When we glue those together, that'll form the two boundary surfaces. So this F cross -1 and F cross 1. So far, we've been talking about topological decompositions of these link complements in thickened surfaces. But we're interested in studying the geometric structure on those complements. So for that, we use the work of Adams et al. And Howie and Purcell. They showed that these link complements are in fact hyperbolic, meaning that they have a complete hyperbolic structure on their complements. Moreover, if our diagram has regular polygons, then that n bipyramid decomposition can in fact be realized as a geometric decomposition. So we can get the complete hyperbolic structure on these complements from that bipyramid decomposition when the faces in the link diagram are regular. So now we need this notion of hyperbolic generalized polyhedra. So our generalized polyhedra with a convex hyperbolic structure. And we're going to say that it has to have totally geodesic boundary. The reason for that is that we want to have just one unique complete hyperbolic structure, and that will allow that to happen. We're also going to use this gear shift map. What that is if we have our generalized polyhedra P plus and P minus, we then glue each pair of corresponding, let's say, K-sided faces via a 1/K rotation, either clockwise or counterclockwise, depending on the checkerboard surface they correspond to. This is called a gluing by a gear shift rotation, right? So if it's white faces glued to another white face, we glue with a either clockwise or counterclockwise rotation, and then the opposite for the shaded face. We'll say that a link is completely realizable if the complete hyperbolic structure on the complement is given by gluing hyperbolic generalized polyhedra by that gear shift map, and those hyperbolic generalized polyhedra have the combinatorial structure of those checkerboard polyhedra. So what this is saying is that we can get this decomposition of our link using the combinatorics from that diagram, And we know how to glue together those two polyhedra. It's specifically by that gear shift map. When we do so, that'll give us this complete hyperbolic structure on our link complement. If, moreover, we have that those two hyperbolic generalized polyhedra have all right angles for their dihedral angles, then we'll say that our link is right-angled generalized completely realizable, or RGCR. A natural follow-up is, well, which links have this nice property? In the setting of links with projections on S2 in S3, Gahn showed that these three links are precisely all of the links that are right-angled completely realizable. So in that setting, all of the links that have this nice right-angled structure. And notice that this implies that no knots have that structure. It's only these three links. And we can see that all of these options have multiple components. All of them are links with at least two components. Gahn also showed that these are the three links that have these two totally geodesic checkerboard surfaces. So they're right-angled, completely realizable, and they have two totally geodesic checkerboard surfaces. We're also interested in thinking about links now on these higher genus projection surfaces. Champonerkar, Kaufman, and Purcell considered links that are in the thickened torus. So there's biperiodic alternating links. These are links which come from Euclidean tilings, which are invariant under translations by a two-dimensional lattice. So they have a quotient in the thickened torus. And they considered semi-regular links, which are these biperiodic alternating links that have regular faces in their diagram. So here we have an example. If we start with this regular Euclidean tiling by hexagons and triangles, we can then realize each vertex in that Euclidean tiling to be a crossing. And we choose those crossings so that overall the link is alternating. Then we can take a corresponding quotient to get this link in a thickened torus. So this link corresponds to this tiling in R3. Champonerkar, Kaufman, and Purcell found that the square weave and the traxial link are the only semi-regular links that have this right-angled, completely realizable structure. And they found that these two links have totally geodesic checkerboard surfaces. So among the semi-regular links, the two links that have these nice properties are the ones built from this tiling by squares and the ones built from this tiling by regular hexagons and triangles. Moving to a higher genus projection surface, we now want to consider our links on, for instance, like a genus 3 surface. So for that, we'd want to start with a tiling of H2. So here we have another example. We start with the tiling of H2 by right-angled octagons. Here we took a fundamental domain of 4 right-angled octagons, and I've shown how you can then glue to get a corresponding diagram on this genus 3 surface. So we can glue these two edges and these two edges. Here we take our result and we fold it to get here. Then you can see how we can close up to get this genus 3 surface. And then we'd insert crossings where these components intersect. This leads us to our theorem. So we have L, a cellular weakly generalized alternating link on F in the thickened surface F cross I. Then the following are equivalent. First, that L is RGCR. Second, that L has two totally geodesic checkerboard surfaces. And then third and fourth, that the diagram of this link satisfies certain conditions. So taking a step back, what this theorem is telling us is that we have this equivalence between having this very nice right-angled structure on the link complement, the link having two totally geodesic checkerboard surfaces, and the link diagram satisfying these different conditions. So those two conditions, first, one of them is that the checkerboard surfaces each consist of one type of polygon, type meaning number of sides. So for instance, one checkerboard surface could have all n-gons, the other could have all k-gons, and it would be possible that n is equal to k. It could be that the checkerboard surfaces actually have the same types of polygons. This fourth condition is that all of these different polygons in the diagram are regular. There's only two types of polygons that appear. Let's say one has n sides, the other has m sides. And about every crossing, we have this arrangement of those polygons in an NMNM pattern. So this is specifying a particular type of condition that this diagram has to satisfy. So if we know that our link diagram satisfies that, then we gain that it has these two totally geodesic checkerboard surfaces and its RGCR. I won't have time to go through the entirety of the proof, but I'll give some of the different ideas behind the implications. So first, we're assuming that our link is RGCR, and we want that to imply that we have two totally geodesic checkerboard surfaces. Well, by assumption, our link has this nice decomposition into these right-angled hyperbolic generalized polyhedra. So let's take that decomposition. Those two generalized polyhedra have these white and shaded faces, right? Recall that that comes from this checkerboard coloring on the link diagram. And what we're going to do is we're just going to glue all of the shaded faces of these two hyperbolic generalized polyhedra together. Well, by assumption, all of these dihedral angles are right angles. So that means that every white face meets its neighboring white face at a pi angle. So this white checkerboard surface that we get is going to be totally geodesic. We could, in turn, glue all of the white faces together, find the shaded checkerboard surface, and see that it too will be totally geodesic by the same process. Next, let's assume that we have two totally geodesic checkerboard surfaces, and we want to see why that implies anything about the diagram of the link. What goes into this are these two results. So first, we show that if our link has two totally geodesic checkerboard surfaces, then the faces of these two generalized polyhedra that its complement decomposes into will be regular. And second, we extend Gahn's work to show that if we have two totally geodesic checkerboard surfaces, then if we have an n-gon and an m-gon that are diagonal from each other with respect to a vertex in the diagram, then n must equal m. So two polygons that are diagonal with respect to a vertex must have the same number of sides. For that first result, what goes into that is first showing that if we have two totally geodesic checkerboard surfaces, then our link is completely realizable. And moreover, those hyperbolic generalized polyhedra that our link complement decomposes into are in fact isometric. So we're saying that with these two totally geodesic checkerboard surfaces, we can cut along those totally geodesic checkerboard surfaces, get this P plus and P minus, and we even have that P plus and P minus are isometric. We can then apply some insight of Gahn's, which is to notice that as we glue P plus and P minus via that gear shift map, we'll see that each face must be regular, because to glue each face to the next without any shearing, we must have that all of those sides have the same length, or at least that we have this isometry, which is this order, however many sided rotation. Now, finally, we're assuming that we have these nice diagram restrictions, and we want that to imply that we have this right-angled, completely realizable structure on the link complement. So we're assuming that all of the polygons are regular, that they're arranged in this NM pattern about every vertex. So start with this nice diagram of the link. And next, we're going to use that geometric decomposition into a collection of bipyramids that are glued together to give the full complement. So on every face, we have now built this bipyramid. And recall that we glue the neighboring bipyramids together along their faces. Well, all of the dihedral angles on these bipyramids come from the interior angles of the face that they were built upon. So if we want to consider the dihedral angle on this horizontal edge D, that's going to be pi minus alpha, where alpha is the interior angle of that regular face this bipyramid has been built upon. So what we can do is we can slice along this edge D, right, which means we're slicing along the checkerboard surfaces. And that'll give us a collection of pyramids that are, we can think of as like above the checkerboard surfaces and below the checkerboard surfaces. We can then build P plus out of the collection of pyramids that we think of as above. And we can build P minus out of that collection of pyramids which are below. As we glue all of those pyramids together, we see that those horizontal edges D have these dihedral angles pi minus alpha n over 2 and pi minus alpha m over 2. where alpha n is the interior angle of the n-gon, alpha m is the interior angle of the m-gon. Well, in order for us to have that original pattern NM about every vertex, we must have that alpha n plus alpha m is equal to pi, and that gives us our result. A way that we can use this work is that it can now show us that those two links that Chempanecker, Kaufman, and Purcell found, this square weave and triaxial link, are in fact the only links in the thickened torus that are RGCR. They asked if there could be other biperiodic alternating links that have this property, and this shows us that there can't. In order for the links to have this right-angled structure, they must have regular faces, and therefore they had to be semi-regular. Then Chempanecker, Kaufman, and Purcell showed that these were the only options among semi-regular links. So far, when we've been looking at this right-angled structure, we've only found links, right? Recall that Gon showed that in the setting of links with projections on S2 in S3, these were precisely the three links that had this right-angled, completely realizable structure. And Chempanecker, Kaufman, and Purcell conjecture that there does not exist a right-angled knot. So there cannot be this link with one component that will have a decomposition into two right-angled polyhedra that glue to give the complete hyperbolic structure on the complement of a knot with its projection on S2 in S3. I showed that this conjecture will not extend to links in thickened surfaces. So if we're now considering links in thickened surfaces instead of links on S2 and S3, we can in fact find an example of a right-angled knot. So here we have this example right here of a knot on a genus 2 surface that is RGCR. Its two faces are right-angled octagons, which I've shown here. So we have the white octagon and the shaded octagon that we can then see corresponding on this link, which if we travel along and note that we glue this boundary component to this boundary component and this boundary component and this boundary component, we can find that our link only has one component, so we found it. Thank you.